Hi, this is Chris Kopak, Assistant Director or Assistant Vice President, Facilities Management at the University of Arizona, also immediate past president for APA. This is our ongoing monthly webinar series that APA has started over the last several years. It's been very successful. Our member survey has shown that all our members are saying this is really very useful information. And I'll tell you, we got a great topic today. We've had the pleasure of having Gary GLEASON from GLEASON STEAM come out to the University of Arizona recently, provided outstanding training to about 80 of my staff, and we thought it would be a great topic to have Gary come out and speak to everyone. And so today's topic, facility steam system, easy tips for a safer, more reliable system. And as always, if you have any questions, feel free to type those up. Gary has a lot of slides we're going to get through in about 45 minutes. We will be taking questions on the last 10 to 15 minutes. So go ahead and type in your questions. And then also remember that CEUs are offered. Billy at our main office there in Alexandria can go ahead and coordinate those to make sure you get your CEUs. So without further ado, Gary, thank you very much. We appreciate this. This PowerPoint and the audio will be put on our APA webpage in roughly about a week. So Gary, I'm going to turn it over to you to go ahead and kick off. Thank you for taking the time to share this information with our members.
Great. Well, thank you, Chris. I want to say thank you to everyone for being a part of this. I know there's plenty of other stuff you could be doing today, so thanks for the opportunity to be a part of this. Sort of getting right into the presentation, of course, our goal here is to just share some simple tips that we've sort of figured out over time on how to improve your heat exchanger reliability and efficiency, correct some common piping errors, avoid water hammer. Of course, we're all concerned with that. Extend the life and maintain accuracy of some of your valves in service, and also to maybe help avoid freezing issues, erosion, or cavitation. So that's our goal, and hopefully we can meet that. We're going to work hard to bring value to you folks today. Steam is universal vapor, and it's said steam is a universal vapor because steam is steam is steam. It's everywhere. It's all over the world, and no matter if you're operating a facility, a college or university, or if you're in no matter what the industry is, no matter what the part of the world you're in, steam is steam is steam. I may actually say that more than once in the next 45 minutes or so, but steam is steam is steam. It's everywhere. So my point there is any issues that you may be seeing or experiencing in your system is not unique to you. It's all the same stuff, no matter, again, where you are in the world. So my question, and I know you can't answer me, but any newsworthy steam system incidents lately that actually made the news, and this one may look familiar to you.
Just after sunrise, a billowing cloud of steam exploded out of the ground right at the start of the morning commute. The blast created a shower of debris and grime.
It felt like an earthquake or something like that.
Left behind, a hole the size of a city bus in the middle of Fifth Avenue, one of the busiest streets in Midtown Manhattan. What did you see and hear?
All right, I heard a boom, and I saw people running.
Officials say the steam erupted from an 86-year-old pipe, one of the thousands of aging pipes that snake beneath the city, providing heating and cooling to 2,000 buildings.
There was asbestos in the steam line casing. That's obviously a real concern to us.
The mayor says the air quality is safe, but officials set up decontamination centers, advising people caught in the explosion to shower immediately and bag their clothes for tests. The blast comes almost 11 years ago to the day when another steam pipe explosion near Grand Central Terminal killed one person. Tonight, officials are relieved this latest blast resulted in only minor injuries. Rahima Ellis, NBC News, Lee.
Now, that one obviously made national news because it's in New York City, as do many things that we see from New York, of course. But we run across, being in the steam business, issues that happen that don't make national news on a regular basis. And so that's something we'll talk a little bit about today as we move forward. So I used to work with an old guy in the steam world. He would say, steam is a perfect vapor. And I'd say, what do you mean by that? He said, well, the point is this, that steam is perfect. It's perfect. We know everything there is to know about steam. We've used it successfully for centuries. So the point there is any issues that anyone may be having in their steam system, guess what? It's not the steam. The problem is not the steam. It's maybe how something was engineered on the front end or designed or installed or maintained or not maintained. Steam is perfect. So getting into the presentation, when we talk about steam, it's really an amazing thing. 71% of all fuel purchased by American industry is used to produce steam. 20% estimated growth by 2030. It's amazing. Steam is not going away. It's growing. It's growing. So it's not going away. BP Energy, every April, they put out what they call their energy analysis. And this is part of that energy analysis. And what they're looking at is, of course, they look at where's our energy going to come from for the next 20 years or so. And this particular slide here is looking at natural gas prices through 2035. And obviously you can see from the graph there that it's trending upward. And so we know in the last several years we've become more and more of an exporter as a country of natural gas. And because of that, we're now competing with the rest of the world for our own products. So prices are going to go up, which directly affects the cost of steam. In the past, maybe 25, 30 years ago, when we're talking cost of steam, about $1.90 per 1,000 pounds. Presently, industry average is a little over $8 per 1,000 pounds. And by the way, just so we're all talking the same language here, when I say per 1,000 pounds, that's pounds mass. Pounds mass. You remember, of course, a pound of steam is a pound of water. A pound of water is a pound of steam, and about a pound of water is about a pint. Just so we're all again on the same page there. So that's per 1,000 pounds mass. And when we talk flow rate of steam or condensate, it's pounds per hour, and that can easily be converted back and forth to gallons per minute. So where's the cost going in the future? Not quite sure, but we know one thing, it's going to go up. And so, of course, the cost of operating our systems is extremely important to us. So according to our DOE, steam is used in 82% of all products produced by American industry, and that's an amazing statistic. Steam is everywhere. It is not going away. As populations grow, so does steam usage. So I say this to folks all the time, that the deal with steam, it's a great thing to be a part of because it is growing. And I also say this to folks all the time in training sessions that we have, is if someone will take the time and commit to becoming the go-to person on steam in a facility, they can write their ticket, because what is going away is the knowledge. So steam is used in all types of facilities besides what you folks do at your universities or other facilities that you where you work. I wanted to point this out because to make the point here that, again, steam is steam is steam, and any issues that you may be seeing on campus there are no different than anything else, any other industry for that matter. But it's used in all types of facilities besides what you do where you work. Some applications for steam, some examples here, a tire plant, as we drive home from campus or from our offices today, we can be appreciative of steam, because without steam, we wouldn't have tires. We use steam in the presses to mold the tires, to vulcanize the rubber, that kind of thing. Wood products, if we're talking about hardwood flooring or laminate or the lumber in our homes, we use steam kilns or kilns with big steam coils to dry the lumber. Pharmaceuticals, one of the beauties of steam is that it's clean, it's odorless, it's tasteless. We can direct inject into food products or pharmaceutical products if we need to. And some of the largest pharmaceutical companies have got some massive steam systems, and so we do a lot of work in that realm also. And then lastly is heating and cooling, which you folks are very familiar with. One example of heating and cooling might be New York City. And what they do there, Con Ed, of course, they produce steam in a central location. Wherever those pipes run around Manhattan is where that steam is going to go, which is exactly what you're doing on your campus. And so it's a big deal. And so New York truly is a city shaped by steam. With that said, this is a slide I threw in here. That's happens to be my family in Manhattan a few years ago, and it was in December. Most families probably get their picture taken in front of the Christmas tree at Rockefeller Center, but I coaxed my family into getting a picture taken by one of Con Ed's steam chimneys or stack. These chimneys, these aren't good things. They're there typically, in many cases, those are steam leaks that we're looking at. And so Con Ed will use the chimney to get that condensate plume up above the traffic, because it can cause wrecks, up above the pedestrians because people can get burned on manhole covers and that kind of thing. So anyway, those aren't good things. So talking about different industries again, the power industry, no matter what the fuel source happens to be, whether it's burning coal or natural gas or wood chips or a nuclear reaction, it all comes back to steam, because we're simply converting that water into steam, running that steam through turbines and turn generators, create electricity. So when you think about it, the computer screen or the projector that you're looking at right now is most likely steam powered. So it's everywhere. Again, not going away. Big term in the industry, cogeneration, or if you're really talking the lingo, it's CHP, combined heat and power. And another beauty of steam is we can do mechanical work with steam. We can run a turbine, which can turn a generator, and we create electricity. An example of CHP or cogen is we can do just that. We can produce electricity. Then when you take that lower pressure steam off the downstream side of the turbine and heat the building with it, or make chicken soup, or make tires, whatever it happens to be, we're simply improving the overall thermal cycle efficiency of the system. And this next slide here is just an example. Another campus. It's a CHP facility, and this particular company is a third-party company that they are, producing steam, also creating electricity, selling the electricity and the steam to this particular university. So CHP, combined heat and power. Corrugators. 92% of all products in North America are shipped in what? Cardboard boxes. So corrugators typically produce steam about 220 psi, and many of them are turning under pressure about 120 psi. And they do that because it's such a competitive cutthroat industry. They have to do that to get all that BTU value and that very, very hot water back to the boiler. So they're burning less fuel to bring that very hot water back up to steam temperature. So colleges and universities, I don't need to educate you guys on that. You're well aware. We do an awful lot of work at colleges and universities around the country. So food and beverage, it's probably the top four of all steam using industries. Food and beverage. We've done a lot of work here recently for a facility in the Chicago area that make a lot of Baby Ruth candy bars there and Butterfinger candy bars. Another facility makes beer or ice cream or bottled water, but steam is everywhere. Healthcare. Hospitals have industrial steam systems just like you do. And by the way, you do have industrial steam systems in your facilities. Just sort of as a side note, the components that you've got in your systems are no different than the components that we would see in what we call heavy industry and refining or pulp and paper. It's all the same stuff, because steam is steam is steam. Pressures may or may not be a little bit different, but it's all the same stuff. Hospitals use it for many different things: sterilization, heating, air conditioning, for ice melting. And I mentioned sterilization. That's sort of a photo there of an autoclave where they sterilize the instrument packs, but all kinds of different applications. Heating, as far as many NFL stadiums are heated with steam. The group that controls the Capitol grounds there in Washington is what they call the architect of the Capitol, the AOC. They're responsible for the steam usage there in the Capitol building. The White House, we've actually been privileged enough to consult on some valves that went to the White House. I've yet to get into the tunnels under the White House, but that would be fun to do someday. But and then the last picture to the left there is Grand Central Terminal. We spend a lot of time in Manhattan. If you've been to the terminal there, of course, they use it for heating. They use it for air conditioning. They have a lot of clients, or I should say they have a lot of customers or tenants. There's an awful lot of restaurants there in the terminal. And it's also up to the guys there at the terminal to provide steam in a clean, dry condition to their customers so they can use it in the restaurants for cooking and so on. So steam is everywhere. Breweries and distilleries. We've done a lot of work with companies like Sierra Nevada, Miller Coors, Hiram Walker Distillery, right there across from the river in Detroit, right there in Canada. So big, massive steam systems. Many of these brew kettles have got what they call a perk ring, and they use the perk ring. And to use their terminology, they say the more vibrant the perk, the more robust the beer. So we appreciate steam in that regard too. The military uses steam. That rapid expansion of volume of steam is amazing. They use that on these carriers in their catapult system, and the catapult actually throws the planes off the deck of the carrier. The jet engines do very little on takeoff. 0 to 165 in less than 2 seconds is pretty incredible. Just as a side note, they have built the last carrier using steam catapults. They've now gone to electromagnetics, not because of reliability, but strictly because of space limitations. They need space. So pretty cool there, I think. The paper industry is a huge user of steam. So we say thank you, steam, when we flip through training guides or we work off of system prints, that kind of thing. So without steam, we certainly wouldn't have that. Chemical manufacturing. Now, this is the #1 industry in what the DOE calls the industries of the future as far as steam users go. And chemical manufacturing, they use it for, especially a lot of these outdoor applications, they use it for steam tracing, where they'll affix a small bore tube to the outside of larger pipes to keep what's in the pipe from freezing, or to keep it pumpable, keep it molten so they can move it. The refining industry, about 57% of their total energy budget is used to produce steam. And a refinery, when you think about it, petroleum refinery is nothing but a chemical plant. They just do it a little bit differently, but they use it for fractionation and hydrogenation, all kinds of different applications there in petroleum refining. And I thought this was a pretty neat application here. This is strawberry production in California, and that's actually a boiler on the trailer there, and they're sterilizing soil in the field. So pretty neat, pretty neat. So again, steam is steam is steam, and whatever issues you guys may be seeing, or you folks may be seeing in your systems, it's not unique to you by any means. So we want to look at a few components in order to improve safety, which is always #1, reliability, efficiency, to reduce the cost, the downtime, emissions, which is a big deal, and ultimately your headaches with your system. We want to understand the system. We want to look at some of the components in the system. So when we're talking about, I mentioned New York City, maybe I didn't mention it, but it's the largest steam loop in the world. And when we talk about a steam loop, we talk about we're actually generating that steam, we distribute. In other words, we get it to where we want to use it. We have the end users where we use that massive amount of energy that the steam carries with it. And then lastly, when that steam turns to water again, when it condenses, we want to remove that condensate and get it out of the system. And hopefully, if we are closing the loop, we want to get that back to the boiler room. So I put the little environmental symbol, the recycle symbol there, because you think about it, in this environmentally conscious world we live in, a steam system done well, there's nothing better, because we're using the water over and over and over again. So again, that's another incredible advantage of steam. So when I talk about the steam loop, here's just a diagram where we talk about the generation phase, which is here in the, in the boiler plant or boiler room. So we're generating that. We distribute that. We get it to where we want to use it. And here's some of our end users. Here's a coil, could be in a air handling unit up on the roof, or a kettle, or a cooker. And it could be in the cafeteria or the kitchen, or at a food and beverage facility. Water heaters, storage tanks. There's a unit heater that could be up in the corner of the warehouse or the shop. And some of that steam tracing we talked about in those outdoor applications. And then all these symbols here, I don't know, what are those symbols there? Many of you know, some may not, but all these little red and black and white symbols, those are steam traps. And steam traps are what I call the gatekeeper between the steam portion of the system and the condensate portion of the system. So they're there. We'll talk a little bit more about them here in a minute. And then to hopefully to close the loop, we want to bring that condensate back to the boiler room, boiler plant, and use that again. So very cost effective to do so in most cases. So here's just some different boilers. We're not talking about boilers today, but just different styles of boilers that fit depending on what our needs are on the generation side of things. And then steam distribution. We can transport steam a very, very long way successfully. We don't necessarily have to superheat it. We just have to pipe it properly and steam trap it properly. Many of you deal with underground systems, tunnel systems, and manholes and vaults. And I will say this, when you have an underground system, it absolutely adds a level of difficulty to what you do. And I tell folks around the world, frankly, in the industrial sector, look, people in colleges and universities can do it successfully underground. How much easier must it be to do above ground? So, again, you guys are doing it successfully below ground. It definitely adds a level of difficulty there. It's just a shot from the tunnel we were in a few weeks ago up in the Cleveland area. This is right there under 49th Street there in New York. So I'm sure you can see similarities between these tunnels and maybe what some of the ones you may have at your particular facility. This slide is it's just from one of Con Ed's promotional brochures to their customers, sort of showing, the manhole, the vault, and just like many of you are doing, all that stuff is in the vault as far as isolation valves, control valves, stanchion joints, steam traps, all that kind of stuff. So definitely adds a level of difficulty. I will say this, no matter whether steam is underground or above ground, steam is steam is steam.
I would let you on ball right now. You kidding me? Couldn't pay me enough to do that, Joel. And you guys wonder why we check. Yeah, Joel, maybe you should step out for a minute.
That was a water hammer incident at a medical center in San Jose, California, about a little over 4 years ago, if I'm not mistaken. That was a water hammer incident. And if your system is making any noise, or if it's moving, it's saying to you, come fix me, because there is an issue there. Water hammer is not normal. We don't mess around with it. Shouldn't be saying that. We'll talk a little bit more about that here in the next little bit. We won't get so much into why that happened, but we can talk some about some simple tips on how to possibly avoid that. So, steam traps. We mentioned steam traps. Steam traps are the gatekeeper. They're everywhere. They are everywhere. And going back to this earlier slide here, we're looking at the traps here, which are these little symbols here. Traps are everywhere. We have one particular user that has an install base of over 64,000 steam traps. Okay, and as you folks know, if a steam trap does not work, nothing works. If a trap doesn't work, nothing works. So I want to talk a little bit about steam traps, and this is going to sort of go right back into what we're talking about, some of the simple tips we're talking about here in a little bit about how to solve some headaches. So why do we need steam traps? So, I've heard it said, because maintenance people need something to do. Well, that's not exactly right. We need steam traps to trap steam in and to get everything else out of the system that we don't want, like condensate or water and air and other non-condensable gases. So the only thing we ever want in a steam system is steam. Traps help us do that. Here's a bucket trap. That is meant to be humorous. Some of you may hopefully have chuckled at that, but obviously that's not a steam trap. So steam trap functions. We don't want them the traps to prevent steam loss, because steam is very expensive, but we want to keep that in the system. We want to remove condensate. Of course, as that steam gives up that massive amount of energy it carries, it condenses. We want that out of the system immediately as it forms. And lastly, we want to remove the air and other non-condensable gases from the system, because air is an insulator. Okay. When we're talking about steam traps, some best practices. The first thing we want to do when we're talking about heat exchangers, or really any application, is determine, is this a non-modulating or modulating application? A non-modulating application is obviously one that does not control or vary the steam flow coming into the unit. In this case here, we've got just an isolation valve feeding steam into the shell and tube heat exchanger, and here's our steam trap here. Point is, we have to be very aware that if we have an elevated condensate return line that is above this heat exchanger, then we need to remember that for every 2 feet vertical head, that's about 1 psi back pressure as the rule of thumb in the steam world. So, and then we can do that. We can accomplish that because we know that our steam pressure is not going to change. We just have to make sure we have enough differential across that steam trap, so when it opens up, we can actually have enough pressure to evacuate the condensate when the trap opens. So, and then on the other side of that, we've got modulating applications where we actually are controlling the steam coming into the heat exchanger. In this case, we've got a control valve, right? So steam's coming in, we're feeding our steam into our unit, and this valve here can ever close down to 0. Bottom line, something we always need to remember is we always must maintain a differential across the trap. So if it is a modulating application where this can close down to 0, we must gravity drain across the trap. Now, if we want to gravity drain into a tank or a pump and then pump it up to an overhead return, we can certainly do that. But just some terminology we need to make sure we're all on the same page with is modulating versus non-modulating applications. Another steam trap station best practice. Let's make sure we can get to the steam traps. This was something we ran across in the last few months where they did a beautiful installation of the steam trap, but if anybody ever has to service it, they're not going to be able to. And if you can't get to it, you're not going to check it, you're not going to service it, and other problems can arise from that. So let me backtrack a little bit too. Notice here I said steam trap station best practices. When we look at a steam trap, we don't look at the steam trap only. There's so much more to it than that. We look at the entire steam trap station. How is it piped? Is it the right steam trap for the application? Is it installed upside down or backwards? Many different things play into a proper steam trap installation, or steam trap station installation, so we need to pay attention to that. So we want to make sure we can install these where we can get to them and service them. Here's an application. We need to, another best practice is make sure they're installed properly, you know, in the right orientation. This particular floating thermostatic steam trap is installed backwards. You know, we're coming off the drip leg here, what they've done, and they're coming into the wrong portion of the trap. So we won't get into that, but you see we tag that with a red tag to say, hey, this steam trap definitely needs some attention. So let's pay attention to proper piping of our steam traps. We want to identify these, and we want to manage the steam trap population. If we're not managing the trap population, bad things can happen. As we said, if the steam trap does not work, nothing works. And in this case, if this steam trap here, the backing up water in the drip leg can cause water hammer problems, not to mention steam quality issues and stuff throughout the system. So let's identify each trap so we know what we're talking about, and let's manage that trap population so we're testing these when we should be testing to make sure that they're operating. It's a very, very critical thing that we pay attention to. We also want to always locate the steam traps below the lowest part of what we're trapping. For example, you can see in this coil application, you know, steam traps are a liquid level device, and they will maintain a liquid level wherever the orifice is in that steam trap. So in this case, maybe the bottom quarter or the bottom third of these coils are staying submerged. So we never want to, we always want to locate it below the lowest part of what we're trapping, and also never install a rise in the pipe ahead of the steam trap. So again, just some things to keep in mind. Another best practice, downstream of a steam trap, we're going to go up a pipe size. So if we're coming in 3/4, we go out of 1. We come in 3/4, or I'm sorry, we go in a 3/4 or 1/2 inch. We're going to come out a 3/4 inch. And so the reason we do that, we have to give the volume of the flash steam somewhere to go. And we won't get into flash steam in this session, but a lot of stuff to be considered there. We need to make sure best practice calls for going up a pipe size. We've got to give the volume of the flash steam somewhere to go. Also, let me encourage you, if you have any steam traps that fail, please do a root cause analysis of failure and figure out why did it fail. And this, we have this particular steam trap in our shop, and you see, here's what the ball in this particular style of trap, a floating thermostatic, should look like. Here's what it looks like. You know, if we put a new ball in or replace the trap with one just like it, what's going to happen to it? The same thing. So let's figure out why did it fail and address the problem. This is a water hammer problem here. So still talking about our steam loop or components within the system, let's look at some of the end users. You know, we talked about some of the end users there. My next slide here is some heat exchangers. You know, the old shell and tube heat exchanger, the workhorse of the steam world. They've been around a long, long time. Some very positive things there. They can handle higher pressures and higher temperatures. Some negatives when it comes to the shell and tube unit is they typically cost more, and they take up more space. And so the plate and frame unit here, some advantages there. They typically cost less. They take up less space. We can do a lot more heat transfer in a smaller footprint. And so they both have their pluses and minuses. They do cost a little bit less, but some people don't like it because they have gaskets between each plate, and those gaskets can leak. And so they get tired of that sometimes if they're not maintained properly. So here's a good example of comparing the shell and tube versus a plate and frame. Both of these heat exchangers, this plate and frame and this shell and tube, do the same duty. And you can see the advantages there. Look at all the space this one takes up, and especially in a university setting, that can be a big deal. So, and not to mention, if you have to service this, when we pull this head off the bundle, we've got to have plenty of room to be able to pull that bundle out to service it. We can also change the number of plates. So if our process changes, we can add plates, take plates away, and it's also serviceable within its own footprint. So that's another big advantage there. Condensate recovery, we're closing that loop. We're bringing that condensate back to the boiler room. That's our goal, if we possibly can. And here's this is a condensate receiver in a particular facility, and if we don't expose that condensate to atmosphere, we can go right back into the boiler with it. So we want to get that condensate back to the boiler room. Something else to keep in mind as we're looking at our steam system is we have to properly support our piping. anchors and guides and supports. And this next slide shows us how not to support our piping. So I can't hear any of you. I hope I got a chuckle or two out of that. But anyway, so we do not support our piping that way. So let's keep it moving on. We talk about steam is perfect. It is perfect. There are zero problems with steam. Steam is invisible. We cannot see steam. And it's also very expensive, but relatively speaking, it's very inexpensive to other forms of energy transfer. Some positives of steam. It is easily transported. It goes wherever the pipes go. We don't have to pump it. So it's very predictable. We know from centuries of use that exactly what it's going to do. You know, at a given certain pressure, it's going to be a given temperature and so on. So it's very efficient. Transports just a massive amount of energy, and we can do mechanical work with it and so on. Some of the perceived negatives of steam are water hammer. You know, from a safety issue, that's something we all want to avoid. It can do a lot of damage to components. You know, the next one is freezing. I've had folks, you know, I've heard them complain, you know, I hate my steam coils. They freeze. Well, it's been said before that coils don't freeze. People freeze coils. And that, again, comes back to how we pipe things. We'll talk more about that. Erosion can be an issue. Steam carrying water along with it is very, very erosive and will cut metal. It will wire draw valve seats, that kind of thing. Cavitation, we'll talk more about that when it comes to some of your centrifugal centrifugal condensate pumps. And it all comes back to net positive suction head required. And lastly is safety. You know, we have ASME B31.1 power piping code for a reason, because people have been injured and they have been hurt and lost their lives as a result of it. So please follow the code in your systems, and that applies to anything above 15 psi. Some examples real quick of some water hammer issues. This is a tube bundle that came out of a domestic hot water application. They'd replaced this bundle 3 or 4 times within about a 1-year period, and we'll talk a little bit about how to avoid that. Here's a floating thermostatic style of steam trap. Water hammer did a number on that. Water hammer did some work here on this control valve body. If your pipes are moving, they should not be. They should not be moving at all. So this is the accident. This is the summer of 2007 in New York City. And they thought it was a second terrorist attack at the time. Here's a crater it left. And some other perceived negatives here. Freezing. You know, again, we need to make sure we pipe things properly, and freezing won't be an issue. Erosion can be a problem. We see an awful lot of neglect in steam systems. You know, I heard one guy say to me about a month ago, he said, "Yeah, I've been here about 12 years. That thing's been leaking ever since I got here." Well, we need to pay attention to that, because as those leaks erode, that steam will erode the metal, and the leaks will get larger. Steam quality is a big deal. It's up to us, up to all of us as facility folks. You know, when that steam comes off the top of your boilers, it is pretty close to perfect. It's nearly 100% dry, and it's a beautiful thing. So it's up to us to maintain that steam quality as it goes through the facility. Condensate lines, carbonic acid corrosion can be an issue. We'll talk about that here in a minute. Cavitation in any of your condensate return pumps can do damage to your impellers, your casings. It can mess up your mechanical seals. And all these perceived negatives of steam, these are all man-made problems. Steam is perfect. So all these problems are man-made problems. We bring it on ourselves. So let's get into the tips. Some simple tips to improve heat exchanger reliability, some of our bullet points. First off, keep in mind when we're talking about heat exchangers, you know, when steam condenses at atmospheric pressure, its volume reduces by about 1,600 times. So let's say we have an application for a heat exchanger. One of the first questions I ask folks when we go in to do an audit or a review of a system is, do you have any tube bundles that are failing prematurely? Many times they're like, yeah, man, this has been killing us. And we'll walk back to it. And so the first thing we look at on heat exchangers is because, let's say we got steam coming to the heat exchanger and we shut the steam off to that unit. And at 1,600 times volume, it reduces to 1 as that steam condenses. So it reduces to 1 and it pulls a vacuum on the unit. It's just like putting your finger over the end of a straw, pulling it out of your soft drink. We're going to be holding liquid in that straw. And that's exactly what's going on, or what can go on in these units. If we hold liquid in that shell of that heat exchanger, 2 negative things can happen. And right there at the liquid air interface on that copper bundle, carbonic acid corrosion can pit out that bundle and cause a lot of problems there, cause it to prematurely fail. And when we bring steam back to it, if we're holding water in that shell, then we can hammer that bundle and do a lot of damage. That's what the photo was you saw a few minutes ago. So what do we do there? This connection here, we walk through plants all the time and we see everything there except what it's designed for. I see a plug in it from the factory. I see a pressure gauge. I see a transmitter, all these different things out of there. But what it's designed for is a vacuum breaker. It's there for a vacuum breaker. It's there to a vacuum breaker simply senses that negative pressure, takes the thumb off the straw, so to speak, and lets the condensate drain out through the steam trap as it's designed to do. So just going with a vacuum breaker there will prolong the life of your tube bundles dramatically if you're not already doing that. And you can see from the drawing there that we can tee off of that and put a transmitter or a temperature gauge or whatever we want to do, but we've got to have the vacuum breaker primarily. This next slide right here is just a demonstration of vacuum, and just sort of setting this up. This is a demonstration. So they've got their steam hose coming into the tank car, and they've disabled the vacuum breaker, and the steam is going to condense. So that's a little overly dramatic. We have seen the after effect of that. So look, let's put a vacuum breaker on our Shell tube, or actually in any steam heat exchanger. Let's put our vacuum breaker there. Here's another vacuum breaker there at the arrow. We want to come off. We have what we call the law of partial pressures, or Dalton's law of partial pressures, where in so many words, it says if we don't have, for example, steam at 100 psi is 338 degrees Fahrenheit, according to the steam tables. If we have a mixture that's 20% air, then Dalton's law of partial pressure says that our temperature is going to be reduced by about 20%. So if you're showing pressure on a heat exchanger and you're not getting your temperature, very good chance you could have air there. So we have an air vent. Here's our vacuum breaker, air vent. So let's have an air vent, because if we don't have an air vent, we've got to push all that air out through the steam traps, and they're not very good at that, only as a secondary means. So air is quite an insulator, as you can see here, 1/1000th of an inch. It's got the same insulating properties as about 13 inches of copper. So we want to use these automatic air vents on all of our heat exchangers to help with that. So real quick definition here, the term saturated means unable to hold or contain more, it's full. So a very misused term in the steam world is saturated steam. Saturated steam is dry. It's not saturated with moisture, it's saturated with energy. And again, it's our job. We've got to keep the steam dry. So we want to follow our steam trap station best practices, use our vacuum breakers and our air vents on our heat exchangers. So real quick, some simple tips to correct some common piping errors that we see all the time. Threaded piping. Threaded piping, if we can help it, should not be used in a steam system, because you think about it, the threads are the weakest part of the piping, and we're expecting those threads to take up the expansion and contraction. And so let's try to get away with that if we can. We need to weld and use flanges if we can do that. We can't always do that for sure. So I mentioned the carbonic acid corrosion in some of our condensate lines. Steam best practice calls for using stainless steel as the material there to avoid the carbonic acid corrosion. So again, some simple tips to correct some of those common piping errors. We want to avoid thread connections, use stainless steel condensate return piping if we can, and of course follow our steam trap station best practices. So some simple tips to avoid water hammer. Evidence suggests that about 2/3 of all premature component failures in your steam or condensate system are due to water hammer. So this was a water hammer incident there, as I mentioned, in the summer of 2007. Here's the crater it left. Here's the piece of pipe itself. That was a water hammer event. And so just a few tips to consider when we're thinking about how to prevent water hammer in our steam systems. Our drip legs must be adequately sized. We'll talk more about that here in a second. Any change of direction in our steam lines, left, right, or up, we want to put an appropriate sized drip leg. And we also want to put drip legs in upstream of any valve that can close, regulator, control valve, isolation valve, whatever it is. If that valve can close, we want to put a drip leg upstream of it. We don't want to crack open large valves. We want to use warm-up valves. And a warm-up valve is simply a small bore valve, sort of, some people may call it a bypass, around any steam isolation valve 3 inches and greater, so we can warm that system up slowly instead of trying to crack open the large valves. So just simply a rule of thumb there is 1 minute per PSI as a rule of thumb. Pipe insulation. If your folks are doing any work on your system and they pulled off the insulation, please put it back on before you crank up, because many times, with less insulation or with no insulation, we're going to generate more condensate. It can easily overwhelm our steam traps. It may not have been sized for that load. And of course, steam traps, we want to make sure we properly size them, make sure they're appropriate, and please test them regularly. The DOE has a steam tip sheet, number 1, entitled Inspect and Repair Steam Traps. The Steam Best Practices Committee for the U.S. DOE recommends testing traps for what they consider to be medium pressure steam, which is from 30 to 150 PSI, monthly to quarterly. Okay, so showing the proper sizing of a drip leg. If our steam header is 6 inches, our drip leg diameter should be 6 inches. Once we get to 8 inches and above, one pipe size below is acceptable. Here's an example of an unacceptable. Here's our steam header that we've got our drip leg coming off of. Drip leg is dramatically undersized there. Same here. Sorry about the quality of the photo, but you can see these are our headers and our drip legs are dramatically undersized. Same here. So this last photo looks good. This was at another university this past summer. Nice sized drip leg, appropriately sized for the application. So to avoid a water hammer, we got to keep the water out of the system. Okay, so we got to follow our steam trap best practices. Let's put in the appropriate number of properly sized drip legs where they should be. Warm-up valves around any large bore, anything 3 inches or greater, steam system isolation valves. Please make sure our pipes remain insulated, and then we need to follow our steam trap station best practices. So now some easy tips to extend the life and maintain accuracy of valves and regulators. Notice here, this is one of the questions I ask folks is, what is that component that we're looking at right there? Well, that is a Y strainer. Of course, Y strainers are installed to protect what's installed downstream. It's sort of hard to tell because many Y strainers in the steam systems are installed incorrectly, or prints show them installed in this orientation with the screener portion facing down. Well, of course, the strainer portion, the screen area here, is there to collect any kind of corrosion material, weld slag, pipe scale, anything passing through that strainer to protect the control valve installed downstream of it. Well, what else collects there? Water collects there. And so when that control valve downstream opens up, it will pick up some of this condensate off of this portion of the strainer. And then two things will happen that will negatively affect the regulator control valve. As it goes through the valve seats, it will wire draw. Actually, it can cut the seats if we're pulling water along with our steam. And secondly, as a percentage of that very, very hot condensate flashes across those seats, it can damage the seats as well. So we want to rotate the strainer to where the screen portion is in the horizontal plane, and that will far extend the life, definitely help extend the life of your regulator's control valves. A couple more things, then we'll go to questions, so hang in there with me. Many of you have pilot operator regulators. Notice this control line. We see this all the time. It should slope down and away from the pilot. Many folks will come up and then down. We don't want any condensate being held up against that, the pilot right there, because it will affect the accuracy of regulation. This next slide is from a university we were in just recently. You can see here are the main valves for the regulators. The pilot's just behind them. You see they're coming up off the pilot and then sloping down. Well, what you don't see in the photograph, over here on the backside on the pipe tee, you know, the springs are different colors for different pressure ranges that we're regulating to for these valves. And there's a whole different pile of different colored springs laying over here where the folks at this particular facility have been changing that spring because they can't get the accurate regulation they need. It has nothing to do with the spring. They've got the right spring in there right now, but the problem is they're not sloping down and away from the pilot. So that's a big deal there. Two more quick things on this. Notice here, they've insulated the bell. These are regulators. They've insulated the bell. We do not insulate the bell. We leave the bell uninsulated because we want condensate there in the diaphragm chamber or that diaphragm bell area because it gives a much more accurate regulation because the condensate is not compressible. So just another tip there. So we got to maintain your steam quality. We've got to follow our steam trap station best practices we talked about earlier. Let's install our Y strainers in the horizontal plane. Let's slope that control line down and away from the pilot. We don't insulate the bell and the regulators. And then lastly, let's make sure when we're talking about freezing, let's install the steam trap below the lowest part of what we're going to be trapping. Let's use gravity. About, I say 90 to 95% of all products of all problems that we deal with in a steam system result from not evacuating the condensate. So let's just use common sense. Let's drop that trap down below the lowest point, and that way those coils aren't going to freeze, among other things. So condensate pumps, cavitation, real quick, I'll make this real quick. It can do a lot of damage to impellers. And what we're talking about cavitation, what's happening here, remember, these are condensate pumps. That condensate is extremely hot. And when a very, very, very hot condensate comes into the eye of this impeller and it sees a lower pressure area in the eye, a percentage of that very hot condensate is going to flash. So now we have a mixture of steam bubbles and very hot condensate here. Well, we can't allow those bubbles to form. So what do? We have to keep a certain amount of liquid head. Let's say right here is our pump suction. A certain amount of liquid level head on the upstream side of that pump to keep it from those bubbles from forming. Every pump you've got on campus, every centrifugal pump, comes with a curve that spells out how much net positive suction head is required. This inverse curve here, by the way, every curve is unique to a manufacturer, to a model number, to an RPM, different impeller trims, different pressures and flow rates. So every pump you've got, please pay attention to that net positive suction head required. Here's just another example. That red part is MPSH required for a different pump, different model number. One of the problems we see here is these standard units are rated to 180 degree water. And so if your condensate is hotter than that, then guess what? Our tank's not high enough. We don't have enough MPSH on the upstream side of the pump to keep it from cavitating. So we're going to have some cavitation problems there. So how to avoid freezing? Install steam traps below the lowest point. No rise upstream of the trap. Follow the steam trap station best practices. Fix your leaks. And please pay attention to MPSH required. So hopefully we've met our goal. We wanted to share some simple tips, things to keep in mind for these things. So just please remember that steam is perfect. It's a perfect vapor. So any issues that you may be having in your steam system, guess what? It's not the steam. So thank you very much for your time. And I know we're pushing it. We've got maybe 5 minutes left. Chris, have any questions come through, and I'll do my best to answer those.
Well, Gary, I'll tell you, this is the first time somebody's been able to get through 140 slides in this period of time. So outstanding presentation, and we definitely got a lot of questions. So we appreciate the knowledge you're sharing. Jeff Fisher has a question regarding, and it sure seems like New York has a number of issues, but what pressure was that in New York when that steam blew?
If I'm not mistaken, they typically, Con Ed typically produces steam at approximately 165 psi.
And Scott now, Calista, what is the expected useful life of a steam system, and what is the general rule of thumb for yearly reinvestment cost?
Oh boy, I may have to answer that one aside from the amount of time we've got. As far as, I'll answer this, when we're talking about steam system components in the steam system, you should be getting at least 6 years of life out of steam traps, regulators, control valves. As far as the components in the system, at least 6 years of life or more. And again, it all comes back to how it's piped. Is it properly selected, installed right, and all that kind of stuff, and is it being maintained? But that's a question that's going to take me longer to answer than we've got, but I certainly can do that.
And what we'll do to all our listeners, any question we don't get to, Gary will go ahead and reply to them, and we'll post those on the APA website in roughly a week. Hey Gary, what do you recommend? Our university systems are dealing with F&A rates, federal government charges on our grants, auxiliary chargings of internal customers. In terms of meters on our steam system, should we be metering the steam coming in or the condensate coming out?
Well, it really, I've seen it absolutely done both ways, and I would encourage if certain universities or folks are not metering, they should be. And the reason being is because when we meter the steam, we hold people in a particular area or even a particular building accountable for that steam usage, and they're not as likely to walk past a steam leak. And so metering is extremely important, but I've seen it done both ways, Chris, as far as looking at condensate back. The condensate back really, I know that there are many utilities that will, what their customers get charged is based on how much condensate they send back for obvious reasons, the cost of the water, the cost of the BTU value that's coming back in the water, and the cost of the chemicals they treat the water with. And so if I've seen them meter coming back, for that reason, but I would say if we can meter steam going out, because if someone's just, if they're losing steam, then they're not getting, of course, it really comes back to personal preference. And I know I didn't do a very good job of answering that, but I can get more into that when I respond by way of email.
No, that's great. Maybe if there's some percentages too, based on the percentage of steam coming back into the system, that's turning into condensate. We'd like to see what that is. Several other questions. We have one here, a great presentation. If there's no water treatment currently, though, what would be the easiest way to get one in the system?
If there's no what?
They're not treating their water at all within their system.
Are they generating the steam, or are they buying it? That would be my first question.
Yeah, they're creating. Well, that's a good question. They don't say. I would have to say they're probably creating it.
Okay. Well, I can't imagine why they wouldn't be treating. That's a whole nother discussion too on the chemical treatment side, and that's a long one. So I'm sorry.
And maybe the short answer on that is, if you're not treating it, you're losing thousands and thousands of dollars, hundreds of thousands, and that could be another topic in itself. Another one we have here. Let's see. How do you size a steam meter?
Good question. And if you've got a steam meter supplier, those guys can do that for you. And there's some good suppliers out there for sure that can they'll take into account all of the considerations there, and they'll size it appropriately.
And you may have to
do that.
You may have to answer this one offline. I know we're going through these quick, but we'll have detailed responses. What condensate recovery rate would you expect of a large campus steam system operating at best practices?
What we're shooting for is 90% return. but 80 to 90 seems to be rather common.
And then, Gary, I know we only have a minute. A quick question, and this is affecting all our universities and colleges and K through 12, and it goes back to the knowledge loss that's taking place. We are losing. You talk about STEAM being perfect, but you have a lot of quality technicians who will be leaving and retiring our systems. Your recommendation for gathering that knowledge to our new folks who are coming in the system, what are a couple key points?
Oh gosh, about how to gather that knowledge. There's an awful lot of knowledge online to be had. You know, yeah, you're right. A lot of the experience is retiring, and you know, a lot of folks aren't coming out of the Navy like they used to. So I would say there's a lot of good information online you can find. Of course, we could always come in and do multiple training sessions for your folks there at your facility.
Well, Gary, we've run out of time. I want to personally thank you for APA. This presentation was outstanding, and I know you have a number of topics related to our utility distribution systems that you provide. We appreciate you sharing your knowledge. Any final thoughts before we wrap it up?
No, I'd just like to say thank you, Chris. Thanks to APA, and thank you, attendees, for your time.
Well, Gary, happy holidays to you, and happy holidays to all our APA members. We're going to take a break from our last Thursday of the month in December, as it's falling right around the holidays. We'll be back at it in January 31st. We'll be coming with a number of topics throughout 2019 already. And again, this is APA's way of giving back to our members very useful information. The presentation that Gary has presented, we appreciate very much, very useful and practical information. And we look forward to continuing sharing really useful information for all our members in 2019. And remember, you can get CEUs on this. So with that said, Gary, thank you. And APA, thank you very much for joining. We had a great attendance on this, and we appreciate it very much. And thank Billy at the APA main office for helping coordinate everything. Have a great day, everyone.
Thank you, Chris. Thank you, everyone. Bye-bye.
Bye now.
Bye-bye. Thanks, Billy.